Thank you. Good afternoon, everyone, ladies and gentlemen. So, as Professor Consa mentioned, now I will present you the characterization of the impedance profiles of nanostructures interfaces between carbon-based nanomaterials and cement hydration products. And actually, in this study, we evaluated for the first time in the literature the electrical conductivity of interfaces between highly dispersed nanotubes and cement hydration products. And for this we used our AFM system, and actually we used the tunneling AFM. So we conducted ultra-low current mapping at sub-10 nanometer scale phases using this system. And for this, actually, we prepared cementitious nanocomposites, cement-based, reinforced with carbon nanotubes at different loadings, highly dispersed nanotubes at different loadings, starting from 0.05 to 0.15% per weight of cement. Here you see the increasing electrical conductivity for this particular type of nanotubes. It is very high. 10 to the power of 6, almost the range 10 to the power of 6 to the 10 of the power of 7. So, we know that interfaces are ubiquitous in cementitious materials and concrete. We have interfaces at the nanoscale between nanomaterials and cementitious products. We have the interfacial transition zone, and we know that the interfaces play a crucial role on the properties of nano-engineered or engineered concrete at the macro scale. Mechanical properties, chemical properties, electrical properties. And from previous presentation from Professor Costa, you saw that the interfaces exhibit unique properties. Exhibit properties that are distinctively different from CSH products and nanomaterials. And we've talked about the chemical and mechanical properties, and in this presentation we will examine the electrical properties, the impedance profile, the electrical conductivity. Here in this slide, actually, we see, what we see here? We see an ultra-low current mapping. It is a nanoscale imaging showing data from current, from passing current. And what we see a 5 nanometer resolution scale AFM imaging topography showing the CSH and the conducting nanomaterial. And we are able to distinguish this from the current mapping. Here we see the current mapping, a range ultra-low current starting from 3.5 picoampere up to 2 attoampere. The light color areas reflect the picoamperes, which actually is the conducting nanomaterial, and the dark areas at the attoampere scale, and attoampere is 10 to the minus 18 ampere. And we are talking for the cementitious products. And actually, in this presentation is divided into two parts. We will see the conductive mechanism in non-percolative and percolative cementitious nanocomposites, and then we will focus on the actual electrical conductivity of interfaces between highly dispersed nanomaterials and cementitious products, and we will have a comparison with when we use the as-received nanomaterials. And here actually we see the results, the resistivity results, electrical resistivity results of cementitious nanocomposites reinforced with nanotubes at several amounts up to 0.5. This is from our previous studies when we examined, when we evaluated, identified actually the percolation threshold. And we found that the percolation threshold, when we use highly dispersed carbon nanotubes ranges between 0.1 to 0.15% per weight of cement. And from experimental data and theoretical calculations, we found that below percolation, when the CNT network forms a non-continuous network, the electrical conductivity is governed by the so-called electron hole because of the non-continuous CNT networks. Once the CNT network is established, a continuous CNT network is established, when we are talking for the percolation threshold and for loadings above percolation, then the current, the electron tunneling, the current passage is uninterrupted through this established CNT network. And for this to evaluate our microscale results, we conducted ultra-low current mapping in our nanocomposites. And we started actually with the plain cementitious materials without any CNT loading. And from this AFM, from this ultra-low current mapping, we observed that no electron mobility, no electrical conductivity can be identified within the insulating cementitious matrix as expected. Here we see the current mapping, a range, a very low, a very limited range from 6 to 3 attoampere. And the majority here is the dark background, the cementitious products. We also see some light spots here, light colored spots, that probably we are talking for air voids that are included in this cementitious matrix. So, the current mapping here in this slide, I will show you the current mapping of cement pastes reinforced with nanotubes at amounts below percolation, at an amount of 0.05% per weight of cement. And here we see the current mapping of our nanocomposite. In the white, light colored spots, we see the current measured on the CNT surface. We are talking for about 3.5 picoamperes. And the brown dark color is the current mapping of the cement hydration products, the CSH. We see here that when nanotubes are included, the current rate is much higher. We are talking for highly conducting nanomaterials with a current of 5 ampere and up, which corresponds actually to 10 to the power of minus 15 ampere. And it goes down to the insulating phase, the cementitious phase, 4 attoampere, corresponding to 10 to the power of minus 18 ampere. We are talking for 3 orders of magnitude lower ampere. So we have an appreciable, a very high ampere rates here to evaluate. And actually, what we see in this picture, we see individual nanotubes dispersed, uniformly dispersed in the cementitious matrix, but with some distances between them. And this is the so-called electron hopping. The electron hopping actually is the electron mobility, the current passage through a non-continuous network. And this is actually governed by the tunneling distance. The tunneling distance is essential, so the current can uninterruptedly transfer through a material. From molecular dynamic simulations and the other simulation in the literature from finite element analysis, we have found a model to calculate the tunneling distance. for specific type of nanomaterials. And here you see the equation, and we did calculate the tunneling distance for our particular type of nanotubes, and it was found between 50 to 55 nanometers. With that said, we need a distance between nanotube equal or less than distance, so we can safely evaluate, we can safely say that we are talking for a percolative network. However, here for this particular amount, 0.05% per weight of cement, we have measured the tunneling distance, this, the average value here, and it was found 105 nanometers, almost 2 times higher than the essential tunneling distance. We continued, actually, we increased the CNT loading in a cementitious paste, and in the right part of this slide, we see the current mapping of cement paste reinforced with the well-dispersed CNTs at an amount of 0.1% per weight. And here, again, the light color reflects the current on the surface of nanotubes, while the black spots, the black background, let's say, it is the current of the insulating CSH products. So here, we see the same range, and this is expected because we are talking for the same material, for the same CSH, for the same nanotube, all right? However, we see that the electrical conductivity, the bulk electrical conductivity of the material is, the bulk electrical resistivity of the material here, 6.3, is lower compared to the 0.05% per weight of cement nanotubes. And this is attributed to the establishment of a continuous network. We calculated from our current mapping here the tunneling distance, and we found an average almost close to zero. And almost close to zero tunneling distance means a continuous conductive network. That means that the ions, the electrons, again uninterruptedly pass continuously without the previously observed electron hopping mechanism. Now, we increased, actually, we know that the 0.1% per weight of cement denotes the beginning of percolation in concrete nanocomposites. And we increased, actually, the amount of well-dispersed nanofibers, and I'm pointing out this, the dispersion, you will see later on in my slides. And here we see the current mapping of cement paste reinforced with dispersed nanotubes at an amount of 0.15% per weight of cement. And we see continuous CNT networks in our current mapping. That means that the electromobility is 100%, is completely governed by a continuous network. Indeed, we see here in my insert, the electrical resistivity reaches a very low value, 4.3 kilo ohms times centimeter. That means that we are talking for a high electrical conductivity. And for this particular amount, we investigated the nanoscale current mapping for the 3 individual phases. Actually, here we see a current mapping of the cement paste reinforced with individual CNT at that particular amount, and we see this image here at the 30 nanometer resolution. Again, the light colored area reflects the current of the nanotube. That means we can see the nanotube, and the dark color area is the current of CSH. And we increase the resolution of this 30 nanometer current mapping here, and we went down to 5 nanometer. So we were able actually to identify 3 different phases based on the current values. Here, in the lower part, the light color area is the surface of CNT. The upper part, the dark color, is the CSH, and there is an intermediate part with a combination of light color and black color spots, which is the interface between the nanotube and CSH. So, using this nanoscale current mapping, this 5 nanometer resolution mapping, we measured the current to voltage. We applied voltage up to 2 volts, and we measured the current at 1 nanometer spots. We used our AFM tip. We control the penetration of the AFM, so we can obtain spots at 1 nanometer edge. And there, at that particular spot, we measure again the current by applying voltage. And here actually, in this graph on the right part, we see the current to voltage curve on the spots, on 1 nanometer spots at the CNT area. And indeed, we found this light color area at 2 volts corresponds to 3.5 plus minus 0.1500. And we used this value here, the ratio actually of current to voltage, and actually the ratio of current to voltage is practically the conductance. We calculated this value, and we use this value to evaluate the electrical conductivity at that particular spot. And actually we are talking for an average value because we evaluated the conductivity in many spots at that particular area. So, by calculating the conductivity, we found the value 3.5 times 10 to the power of 5 Siemens per meter. And we correlate actually the value that we obtain with the nominal intrinsic conductivity that was provided by the manufacturer of the CNTs. And you see here that our calculated conductivity is very close to the nominal intrinsic conductivity of the nanotubes. We continued by evaluating the electrical current mapping here for the green, the yellow spots here for CSH, 1 nanometer spots. We measure the current, and we see that while the pattern of the 2 curves is the same, we practically talk about 6 orders of magnitude lower current at the same voltage. That means that at 2 volts here, the CSH exhibit a current of about 5 attoampere. And we used actually this current here to calculate the conductivity that was found 1.25 Siemens per meter. Orders of magnitude lower than the superconducting carbon nanotubes. Now, if we want to correlate the nanoscale results with the macroscale findings, we will have this slide here, this correlation. Actually, on the right part of the slide, we see electrochemical impedance spectroscopy measurements of 28 days cement test with this water to cement ratio of 0.5. And actually here we see a typical Nyquist plot that reflects the real part of impedance, which is known as resistance, the horizontal part, and the vertical part represents the imaginary part of impedance, the electrical energy absorption capacity of the material. Right at the cusp point, the material acts as a mid resistor, and it can be used to evaluate the real electrical conductivity of the cementitious material. And indeed here, from our calculations, it was found that the bulk conductivity of the material is 2.1 Siemens per meter. You see here also the electrical conductivity of CSH, 1.25, very close. Then, to continue here, as Professor Kosa mentioned, the interfaces exhibit unique properties, chemical, mechanical, and now we will see the electrical properties. We measure the current right at the area between the CNT and CSH, the interface actually, and here you see the results of current versus voltage in this green curve. And you see here that the current is almost 4 times higher of the interface, is almost 4 times higher than the current of CSH. And we calculated here the electrical conductivity of interface, and it was found 5.32 Siemens per meter, almost 300, more than 300 higher than the conductivity of CSH. We evaluated our results also by conducting ultracurrent mapping at that particular type of CNTs, at that particular loading of 0.15% per weight of cement, using as received without any dispersion. And in this picture here, you see the CNT agglomerates. And actually, you see, we reduce the resolution of this image, 500 nanometers, so we can see the agglomerates. But to investigate here, to evaluate the electrical conductivity, we scale down, we increase the resolution, we go down to 5 nanometers here. And in this current mapping, you see the area of the CNT surface and the area of CSH. Now, using this current mapping, we evaluated the electrical conductivity of, I will go back here, of this area here at 1 nanometer intervals. So, we measured actually the current and we calculated the electrical conductivity, and we see that for the first here 27 measurements, we found an electrical conductivity that corresponds to 3.5 times 10 to the power of 10 Siemens of meter. And this is the conductivity on the surface, measured on the surface of CNTs. After passing this point, you see that the conductivity sharply decreases here without an intermediate location. So, intermediate electrical conductivity values sharply decreases, showing a value 1.25, and it continues at the end, let's say here, of our current mapping. And you see here that there is an intermediate state between CNT, the electrical conductivity of CNT, and the electrical conductivity of CSH when nanotubes are used without any dispersion. So, to conclude here, we saw that the interfaces between highly dispersed nanotubes and CSH exhibit a unique morphology and electrical, chemical, and mechanical properties. we need a complete dispersion and exfoliation of carbon-based nanomaterials for establishing continuous conductive networks, which is essential for an uninterrupted current flow, electromobility. We found that the percolation threshold of CNTs ranges between 0.1 to 0.15% per weight of cement, and the ultra-low current mapping is a useful tool for identifying the tunneling distance, which is essential for the evaluation of the bulk electrical properties, electrical conductivity of nanocomposites. And the dispersion, again, and exfoliation is crucial for establishing interfacial areas for the effective current transfer between the conducting nanomaterials and the insulating cementitious. Thank you very much.